So this is part 2 of the chapter 3, section 11, notes on related rates. I forgot to give you, excuse me, the other type, and that's going to be when you use trig functions. So I'll give you 2 examples of trig functions and we'll be done. Should be a quick video. So example 1, you have an observer right there, and he stands 200 meters, so they labeled that distance as 200 meters from the launch site. So the balloon is launched from this point. And you have a hot air balloon. And the hot air balloon rises straight up vertically at a constant rate of 4 meters per second. So let's take a look at that. It's a rate, so we know it's a derivative. So when it's a derivative, we know something is changing as something is changing. And so we have to figure out what's changing. So the top is a distance. What distance is changing? They've already labeled this for you as y of t as the distance. Now, if they didn't, you'd have to choose and realize, hey, this length is changing. I got to give it a name. They called it y for you, but if they didn't, you would have to come up with a variable for there. And it says time changes because you see it's a distance per time. And we know that that is 4 meters per second. Now, is it positive or negative? This is where you have to think. If y is increasing, the derivative should be positive. Since the hot air balloon is moving upwards, y is increasing, so the positive answer is fine. Now the next part, how fast is the angle of elevation of the balloon increasing? So again, this is interpreting. What does that mean? It's asking for a derivative. It's the rate at which the angle changes. So you're going to have to take the English and translate it into calculus. So something's changing as something changes. It's a rate. How fast is the angle changing? The angle of elevation is just from ground level, the angle is above the ground level, and that's the angle of elevation. They've already determined that that's theta. So I'm going to put theta over time, and they want that at 30 seconds. So they want that when t equals 30, and that's your question mark. And so those are the details. And so you need an equation involving these functions, y and theta. Well, I'm going to redraw this triangle because with all the pictures, it's kind of cluttered. It's hard to see just the basic stuff we have here. Let me try that triangle again. There we go. And let me label these. So we know that's theta, and this is y of t, and that's 200. So we need a function that involves theta and y. What can we do? Pythagorean theorem's not going to work. We talked about how that was a possibility. We talked about area. There's nothing about area, nothing about volume, so it's not that. Similar triangles, we don't have similar triangles. So the one that I forgot to mention was trig functions. Is there a trig function? And you should see that this is the opposite and adjacent of a right triangle. So opposite and adjacent is tangent. So we have the tangent of our angle is the opposite over the adjacent. And there is our equation. So now, if we take the derivative, we'll end up with rates. And hopefully you agree, y changes over time because the balloon is moving up. And theta changes with time because as the balloon moves up, theta is going to increase. So both y and theta are functions. Our variable is t. So when we take the derivative, we need to treat these as function or as box in our chain rule. So the question, what is the tangent of box, derivative of tangent box? It's going to be secant squared of box times the derivative of box for the chain rule. And 1 over 200 is a constant. So the derivative of y, by definition, is just dy dt. Okay? So there is our equation that we're going to use. We know that t is 30. Whoa. We wanted a t is 30, I should say. So I'm going to rewrite these and say I want this when t is 30. When t is 30. It's kind of hard to see, but we'll deal with that. Now we have to fill in everything we know. dy dt, that's 4. That's easy. That's always 4 meters per second. 1 over 200 is a constant. That's not going to change. d theta dt, that's what we're trying to find, so I'm going to leave that there. Here's the tricky part. What is secant squared of theta? How are we going to get that? Well, secant squared is 1 over cosine. So to make it not as complicated, I'll go ahead and write it 1 over cosine squared theta. But what's the cosine of this angle? How am I going to find that? Well, cosine is adjacent over hypotenuse. I don't know the hypotenuse. What am I going to do? But the key for this one is when t equals 30. When t equals 30, where is the balloon? Well, let's look. The balloon rises 4 meters per second, right? The balloon moves up 4 meters per second. So after 30 seconds, when t is 30, y of 30, what would that be? That's going to be 120 meters. So now we know at the particular time when t is 30, y is 120, and we know x, because it's constantly 200. Using Pythagorean theorem, we can find the missing side. So this missing side here would be square root of 1 of the legs squared plus 1 of the legs squared. And now we can find the cosine adjacent over hypotenuse. So check this out. Cosine we replace with adjacent over hypotenuse. We're almost done. Okay, actually, you know what I should have done? I'll do it now. The 4 and the 200 reduce. That's going to go in 50 times in the bottom. So that's much better. 1 over 50 meters per second. Now, this, I multiply by the reciprocal, and that whole thing is squared, by the way, too. I am messing up. It's cosine squared. So I'm going to square that and flip it. I'm going to end up with 200 squared plus 120 squared over 40,000. And that's 1 over 50 meters per second. I've been negligent on my units, but we're okay. Now to get rid of this, I multiply both sides by its reciprocal. And I get my final answer. It's going to be 1 over 50 times 40,000 over 200 squared plus 120 squared meters per second. It's not going to be meters. There are some units here, like I said, that I have not been paying attention to, and I kind of messed up. But the meters should have canceled out. It's going to be radians per second. But that is the answer there. Hopefully, it's correct. I'm not going to simplify that. I'll leave it like that. You can pop that in your calculator if you want, and we can see if that comes out right. This is the second example. So you have a lighthouse. There it is on an island. 500 meters, they label that from the shore. So point P is that perpendicular point on the shore. Q, we are told, is 200 meters away from P. And we're told this light beam is spinning in circles, right? It's rotating. How fast is it rotating? We're going to talk about that. So that thing's rotating 4 revolutions per minute. We're told that right here, 4 times each minute. And we want to know the speed that the beam moves when it strikes Q. So this beam is moving this way. How fast is it moving at the point Q? So now we need to make some definitions, talk about things. So if we're talking about the speed of this light beam moving, its distance is changing over time. What distance do you want it to be? So I'm going to say the distance of that light beam, we have to give it a name. I'm going to say the distance from point P, I'm going to call that, what should I call it? L for light beam? I like L. Okay? And so they want to know how fast L is changing as time changes, specifically when L is 200, because they told us something. The shore, what is the speed of the beam when it strikes Q? So we want to know when it gets here, how fast is the beam moving? Well, there, L would be 200, because we're told it's 200. Okay, what other rates are given? Well, right there, that's a rate of rotation, right? 4 revolutions per minute. And this is where you have to think again. What is going on? So 4 revolutions per minute. Each revolution is 2 pi. That's 8 pi radians per minute. Now, if you look at that, that's a rate of change of an angle. So what they've really given you is d theta dt is 8 pi radians per minute. So now we have another situation here where we have an angle. That angle theta is changing. As this rotates, how fast does theta change? 8 pi radians per minute. So now we have L and theta. What are we going to do? So I'm going to draw this triangle down below so you can kind of get an idea of what's going on. We have theta up top. That's constantly 500, and this is L. So this is opposite and adjacent. Again, we're going to get tangent. They're going to tangent us. So we know that the tangent of our angle is the opposite side over the adjacent side. And this is going to be very similar to the previous problem. We're going to take the derivative. Now, theta changes with time and L changes with time. So both of those are considered functions. So in our derivative, we treat them as box for our chain rule. What's the tangent of box? That's going to be secant squared box times derivative of box. I was actually hoping for a different type of trig function, but this will do. 1 over 500 is a constant, and the derivative of L, by definition, is dl dt. And we want this specifically when L is 200, right? We're told at Q, which L is 200. So I'm going to say at L equal to 100 on both of these. And fill in what I know. So do I know d theta dt? Yes, I do. 8 pi radians per minute. So that's 8 pi radians per minute. 1 over 500 is a constant. dl dt is what we're looking for. Now, secant squared theta, I'm going to change it again to 1 over cos squared theta. So I need the cosine of this angle, which is adjacent over hypotenuse. Okay, at what point? This one's a little easier. Do we know L? When L is 200. So we're going to get an L of 200, and that's going to make the hypotenuse 200 squared plus 500 squared, square root. So cosine is going to be adjacent over hypotenuse. 1 over adjacent over hypotenuse, and that's squared, times 8 pi radians per minute, 1 over 500. dl dt is what we're trying to find. And basically, I just multiply both sides by 500. I am done. Oh, I'm going to flip that and square it. So if I flip it and square it, I'm going to get 200 squared plus 500 squared over 500 squared. And we have 8 pi. I multiplied both sides by 500. Actually, the units here are not correct. We had minutes. So this is per minute. If you want to convert to seconds, you'd have to multiply by 60, right? Or divide by 60. Actually, this is per minute. So if you want seconds, you'd have to divide by 60, I think. You can figure it out. All right, that's it.